Greetings. This is Graham Warren, working with you on a simulation, an AnyLogic simulation of a serial Jackson network. I'll run it and we'll take a look at it. So the first clip is going to deal with basically explaining the Jackson network and looking at the results and doing some interpretation. And then the second one, I'll come back and talk about how you would set this up in AnyLogic and poke around in the actual blocks that you drag and drop on the canvas in AnyLogic. All right, so a Jackson network is a collection of exponential servers connected in some fashion. They are routing of flow units inside the network is probabilistic. Any exogenous arrivals to the Jackson network are in Poisson processes. So you've got this exponential inter-arrival time, exponential service time characteristic of these Jackson networks, just one type of flow unit. In our particular network, we're looking at a serial Jackson network where we've got arrivals coming into the network in one Poisson process at the rate of 10 per hour. They hit the first station where they get exponential service at the rate of 20 per hour. Then they hit the second station where they get service at the rate of 30 per hour. We've got, I'll talk about the details of this, of setting this thing up in the second clip, but we've got 4 KPIs that are of interest here. Let me advance this just a little bit. This thing simulates for, I think, 3,000 minutes, and it runs around 200 customers. So I'm going to just accelerate it to the point where we can pause it, where we've got reasonable distributions formed here. So I'm at, let's see. Pause it around here. Okay, so 128 customers have gone through. So the distributions are still, evolving, but you can get a sense. So 4 KPIs, you can see the average queue length at the first station, 0.778. At least that's the current estimate off of 734 samples. I guess that's 734 time units, 734 minutes sampled. Much shorter queue at the second workstation, 0.118 on average. And you can see why that may be. You've got faster service rate here at the second station of 30 per hour. So you'd expect there to be a shorter line versus the first station. In addition to these average queue lengths, we've also got some distributions of times. This first one is the flow time in the system. That is from time of arrival to completion of service at the second workstation. And then also the time in the first queue only, not in service. Okay, so the time in the time in service, both in service and waiting at the first workstation. All right, so that averages out at 9.26 minutes to clear the system overall. And then the time at the first workstation is 6.25 minutes. So the balance, about 3 minutes and 1 second, according to current estimates at workstation 2. And again, that difference is being because of the 20 versus 30 per hour service rates. Okay, so we could use we can confirm Little's law at each of the stations. We could also confirm Little's law holds across the whole network. And this is a very simple Jackson network, serial Jackson network simulation. Maybe I should just hit the controls here. This right arrow is to run the game, run the simulation. This is to stop it. Not sure what that is, but this slows down or speeds up the simulation. And if you want to fast forward all the way to the end, it will do that. I think when it runs all the way out to 3,000 minutes, it actually shuts down with a fatal error, but not too important because we have demonstrated everything we need here. All right, I'll come back in the next clip and walk you through the actual model.